We are now in the final topic of our lesson 6. No, this is the general response of a second order system. Here is the general second order transfer function. No, this one, as we could see in this table. No, the first transfer function here. This is the general second order transfer function equation. And it could have any pole zero plot and any shape of response curve according to the specific given value. We're going to discuss more about this later. Let us first try to look at the other types or classification. Now, the second here is the overdamped system. We have the third one, underdamped. Okay, let me scroll through for now. We have undamped and we have critically damped. Now, for us to recall immediately, I want you to take note first about the equation of the critically damped. By the way, these four other types are the special cases of the second order system. All of them are second order system. Aside from the general equation, these other four are special type. So the first one is critically damped. Notice that the polynomial in the denominator is a perfect square trinomial. No? Have you noticed that? So the square root of 9 is 3. 3 times 2 is 6. No? So it's the perfect square trinomial. And notice also that the numerator is only a constant value that is equal to the value here. So that is called a critically damped. The undamped is the one which has no middle term. No? So that is undamped. Another is the underdamped. So if you have noticed, the middle term is 2s and 2 is below 6. No? For 6 for the critically damped. So if it's below, then we call it underdamped. And while this one, overdamped, the middle term is higher than 6, which again, 6 is the middle term of the critically damped. So since it's higher, then that is overdamped. Now, let us try to look at the pole and zero plot of each of these special types of second order system and their corresponding responses or output response curves. Okay, so for the zero plot, notice here that we're going to have two poles, negative poles, okay, at the real axis, real number. So this will be the time response equation, CT, okay, with the two poles here. For the underdamped, notice that we have two poles, but they are in the imaginary line. That's why their values is j square root of 8 and negative j square root of 8. And this is the time response equation, and this is the time response curve. Okay? So, have a particular observation with regarding to the term, the name, and their response curve. Okay, so for the overdump, it has that shape. For the underdump, okay, so it has this oscillation. For the undumped, okay, so for the pole and zero plot is again, it has two poles within the imaginary lines, imaginary values. And this is the time response equation. And note that its curve is a sinusoid. Okay? So that is undamped. Now for the critically damped, again, it has two poles that are equal and in real values, real number. So once more, this is the time response equation and the response curve. All in all, they were drawn in a single graph for comparison. So we have here the critically damped, this one, and as compared for this critically damped, the overdamped is somewhere below the critically damped, and the underdamped is above, the critically damped. So the underdamped somewhat has some oscillation, while the undamped, it's a full sinusoidal wave, meaning there's no damping. Okay. So here are the summary of the observation, and description of the four types, of natural responses of the second order. So the first one is the overdamped. As you have noticed earlier, it has two real poles, okay, of different values. Okay, so the natural response, two exponentials with time constant equal to the reciprocal of the pole locations. So here it is. For the underdamped, it has two complex poles. Okay, so the natural response damped sinusoid with an exponential envelope whose time constant is equal to the reciprocal of the pole's real part. So the radian frequency of the sinusoid and the damped frequency of oscillation is equal to the imaginary part of the poles. For the undamped responses, so the poles has two imaginary, and the undamped sinusoid with radian frequency equal to the imaginary part of the poles. And lastly, the critically damped, it has two real poles, of the same value. So one term is an exponential whose time constant is equal to the reciprocal of the pole location. So another term is the product of time, t, and an exponential with time constant equal to the reciprocal of the pole location, or given by this equation. So let us have this example, to practice if we could easily identify the types of this given their transfer function equation. So the first one, we first need to identify if this is a perfect square trinomial. So what is the square root of 400? I think it's 20 times 2, it's 40. So 12 is below 40. So ano siya dapat? It's underdamped. Okay? So for 90, the square root of 90 is 30. 30 times 2 is 60. So it's overdamped. Yes. And 225, the square root I think is 15 times 2 is 30. So that's perfectly trinomial, critical damped. And lastly, of course, the undamped.